So I asked you guys to jump in on a poll, and here are the results. So you've got Valentine's Day is not quite as exciting to a lot of people as the Super Bowl. And some people say neither, some people say both. How does that compare to the national poll that they did? Well, here's the national results. So I think we're a far cry different than what the results were nationally, but you know, that's to be expected. We've only got maybe 30 some people or 40 people in our poll, whereas this poll is based on 1,257 individuals. Now, 1,257 individuals sounds like a lot, but when you compare that to a nation of nearly 350 million people, that's a small fraction. It's remarkable, though, that they can do a good job of estimating what people think with such a small poll, relatively speaking. I mean, it's just a tiny fraction of how many people there are nationwide. So let's look into that a little bit further. Now, the goal of polling, our goal is to try and get information on a population parameter. Goal of polling to get information about a population parameter. Now, it's been a minute since we've discussed population parameters, so maybe we should remind ourselves, and feel free to unmute yourself and jump in. What's a parameter? What is a parameter? No one? All right. So a parameter
applies to the whole population.
All right, excellent. Parameter is a numerical characteristic or summary. Let me put a numerical summary of a characteristic of a population. The key thing here is that it's of a population. We're not just dealing with a sample, we're dealing with a population. So it's everybody. So let me underline population. How's that different than a statistic?
A statistics of a certain group.
Yeah, thanks, Cam. So a statistic is a summary of sample data. And I should probably put numerical summary. Of sample data. So one means you have to conduct a census. That means you have to look at everybody in your population. Whereas if you're dealing with just a sample and you calculate a statistic, well, you don't need everybody. You don't need your whole population in your sample. Now, there's a lot of different things you can calculate when you work with statistics. There's the mean, standard deviation, and finally, something we haven't really worked with much, which is the population proportion. And I want to look at this in kind of this fashion, a little comparison chart. So we'll start off with samples and remind ourselves of the notation, and then look at parameters. So sample, and that's going to be your statistic. And then a population goes along with parameter. What's our notation for the sample mean? What notation do we use there?
Mu.
Mu, all right. Now mu is the population parameter. So if you had all the data, if you're actually able to conduct the census, then you would get a calculation we would refer to as mu. But maybe you just have a sample. So what's our sample mean going to be denoted as? Does anyone remember that one?
X bar.
X bar. Thank you. X bar. Sample standard deviation, that was S. How about the Greek letter that we use for our population parameter? What's the symbol over here for the standard deviation? What's the
Is it
Greek letter?
sigma?
Sigma. Yeah, well done. Now, one that we haven't really worked with, but we're going to work with moving forward is your population proportion. So, for instance, I think, was it 28% of us? 27% of us thought that Valentine's Day was a more exciting February holiday. Okay, that's great. That's a sample statistic. We would denote that with P hat. Now, annoyingly enough, P and P hat and things that look a lot like this are going to get used a lot for the remainder of the course. But at least right now, our population proportion, our proportion, I guess I should get rid of the population part. Our proportion is P hat for a sample and P for a population. So again, you've got a difference between your sample statistic and your population parameter. What you're hoping, because it's not realistic to get data for everybody, especially if you're looking at something as inconsequential as what's your favorite February holiday. You're hoping that this is a good estimate of this. This is a good estimate of this. This is a good estimate of this. But all of these, the left estimates the right. And in sampling, we hope that your population, your sample statistic is a good estimate of your population parameter, whatever it is. Now, in our case, it wasn't so good, but that's probably because we don't have a representative sample. So how come it wasn't as good? Well, for instance, most of you people live in the same geographic area. You're roughly the same age and roughly the same level of education. So that's going to make you different than the complexion of the United States as a whole. So you shouldn't necessarily expect to get the same answers if you don't have a good representative sample. So not a surprise that we were a little bit different than the national average. Now, let's look at this handout in particular and get a little bit more comfortable with estimating things. Now, this is going to be an artificially small example because I want to make a point out of this. So let's keep track of some things here. This is going back to a data set that we used when we introduced standard deviation. And I talked about the heights on the starting five on a basketball team, completely fictitious. 86 inches would be incredibly tall. Anyways, if you were to actually calculate the mean of this population, and this is your population right here, just those five, the mean height of these players is 80 inches. Now, suppose that this is my population, but I want to get information about it by sampling. And that's the goal of sampling, is you're trying to find out information about a population parameter. So suppose I don't know that this has a mean of 80, but I want to try and figure out roughly what the mean could be. I could draw samples of size 2 for my population. Now, admittedly, it means, you know, samples of size 2, it's like, really, you're being that lazy, you don't want to poll everybody? And the answer is yes, but just for purposes of illustration. Now, the first question I want to ask you, and you can open up a Google Sheets for this, is how many ways are there to choose 2 people from a group of 5? Okay, so let's open up a Google Sheet here. And let's see here. Let's see, Sheets. And let's just open up a blank one. Okay. You remember the formula for combinations? Combin of, it should be 5, 2. Combin of equals combin 5, 2. So there's 10 different choices I could make. If I'm gonna sample just 2 people from this population, there's 10 different ways I can do it. So let's write that down. It's a big 10 right here. And here is all 10 of those possible samples. If you get 76 and 78, you add those 2 together, divide by 2, that's your sample mean. So that's your X bar. If you get 76 and 79, you get 77.5 and so on, all the way down. Now remember, our goal is to try and figure out roughly what that is by sampling, because it's not practical to always do a census and get data from every element of a population. So, all right, we'll just assume that we're sampling for sizes of 2. We actually did land on the correct value once, right? See it down there? That actually happened to be the correct value. So for that sample, we nailed it. But overall, some of the values were low, some of the values were high. It just kind of depended on chance. The value of X bar, your sample mean, depends on chance. Now, if you look at those values, here's the heights of the players to begin with. You've got all those down here. And here's what happens when we have samples of size 2. You're trying to estimate the population parameter, which is mu. And you get values that are all over the place. In fact, seems like I'm missing one. Should be one right here on 80. So let's put that there. So we got lucky ones, but overall, some of the values are high, some of the values are low. Some are good estimates, some are not so good. But all of them are trying to estimate this number down here, 80, the population mean. Now, there's something interesting that I want to point out here. If I total up my data, if I total up all these various sample means that I got from drawing 2 out of that population of size 5, I get 800. If I get a total of 800 for these 10 numbers, what's the average of these sample means?
$80.
80. Remember, X bar is the sum of your data divided by n, which is 800 divided by 10, and that's 80. Thank you. So we get 80. Now that's kind of a coincidence. And we're trying to estimate the population mean. And even though we don't often hit it with our sample mean, this is saying on average, your sample mean's not a bad guess, because on average, you're going to get the right number. So interesting. Let's move on for samples of size 3. And that's the next column over here. So that's this data right here, samples of size 3. And for samples of size 3, there's a total of 10 of them. You can do the same calculation that you did up above, 5, choose 2. Choosing what 2 are in is kind of the same thing as choosing what 2 are left out. There's going to be 10 of those. If you wanted to, you could calculate the mean of all these sample means. You get these numbers. And once again, we got lucky, right? We actually hit it spot on right here. Okay. But overall, you're not really going to get lucky very often. One time out of 10, you're actually going to get the right number. Those values are down here. Here's your samples of size 3. Now, something interesting is happening. If you're trying to figure out what the mean is, these are your guesses for size 2. These are your guesses for size 3. Which guess tends to be better? Samples of size 2 or samples of size 3?
3.
3, right? Because even on a bad guess, you're closer than some of the guesses down here. Now, some of the guesses are really good here. You know, they're not all so good, but that's okay. What is it in our vocabulary that we can use that describes the spread of the data here? What talks about the spread here?
Distribution.
All right. There's another more specific word that I'm looking for.
Oh, standard
Distribution's kind of part of
deviation.
it. Yeah, the standard deviation. So the standard deviation here is bigger than the standard deviation here. So that's something to keep an eye on. And we'll learn more about that in section 6.4. For now, let's take a look at our last column of data, which is for samples of size 4. Now, if you're curious, how many samples of size 4 can be chosen from a group of size 5? Well, choosing 4 out of the 5 is really like choosing which one gets left out. And there's 5 different choices as to who gets left out. So, okay. Did I get lucky on any of these? Did I hit exactly the population mean?
No.
No. But I think I'm getting closer. This is n equals 4. And for samples of size 4, well, generally speaking, unless you get really unlucky, generally speaking, you're going to be really close with your guess. And that's the whole point. We're trying to get close with our guess. We want to get close to the population mean with our best guess of the population mean. X bar, the sample mean. X bar is our best guess of the population mean. Let's look back at something that I overlooked. For samples of size 3, if I total all these up, I get 800. What's the mean of my sample means here?
80.
80. Yeah, same as the last one. 800 divided by 10 is 80. How about over here? When I total these up, I get 400. What's that say about the mean?
80.
80.
It's 80 again. Wow. That's starting to feel like something that's not really a coincidence. So, you think it's a coincidence that every time we calculate the mean of these sample means, that we get the mean of the population mean? Think that these are all the same by coincidence? The answer is no. And what's going on here is that X bar is what's called an unbiased estimator. X bar, the sample mean, is an unbiased estimator of the population mean. There's some other conclusions I want us to get here. Well, I'll give you a second more to copy this down.
Can I ask a question really quick?
Yeah, please do.
I guess I'm having trouble understanding like the purpose of why we're doing this. Like, why are we using these different sample means? Like, what is the difference between just finding the mean and doing what we're doing
Great
here?
question. Let me go back to this here. Typically speaking, you can't calculate a population parameter. So the question that I started this class off with was, which February holiday means more? We could do a sample and, you know, you can look at the nationwide sample. But would this be the exact thing that I would get if I talked to everybody? Maybe not. Now, is talking to everybody about such a matter, you know, as terms of which is your favorite February dates, Valentine's or the Super Bowl, is that very practical? Probably not. Probably not. So instead of talking to everybody, which requires a census and is really next to impossible for us, the best thing that we can do is do a sample. And so back to your question, what I want to show is, well, what happens when I'm sampling and using that sample as an estimate of my population parameter? Because typically speaking, your populations are much bigger, and you can't actually know this value. The best thing you can do is estimate it. And so I want to understand the behavior of this estimator. What happens when you use X bar to estimate a population mean? And so it's a great question, Skylar. Let me try and hone in on the answer a little bit more. A couple things have happened in using these different samples, different sample sizes to estimate our population mean. So for convenience, I'll call this X bar sub 2 because it's the mean for sample size 2. And this would be X bar sub 3, and this is X bar sub 4. These are all your different possible sample means for samples of that size. And here they are plotted. Now, one of the things that we saw is that on average, even though these values are scattered around the true population mean, on average, they give you the true population mean. This, if I averaged all these together, give me the true population mean, and so on. So that's why I said that X bar is an unbiased estimator. Now there's something else that happens. As you increase the sample size, the standard deviation of these numbers decreases. Meaning that as you increase the sample size, you're getting a better and better guess as to what this actually could be. Because when you look at the first sample size, it says, oh, well, the mean can be anything in here. And then you take a look at the next one, and it says, all right, well, the mean's probably in here someplace. And you take a look at the third one. It says, all right, my mean is in here. So as you increase the sample size, you're narrowing down where your search for this could be. Could be any of these values or something in between, but it's going to be in here. So by increasing the sample size, you're getting a better guess as to what this could be. Because in general, you don't know what that is. It's just we're dealing with an artificially small example, so I can try and bring out these characteristics. And by the way, I should have had that over here like that. So we're trying to figure out what's the behavior of X bar. Does that help?
Yes.
All right, that didn't sound convincing. If you want to follow up with another question, please let me know. This is a hard subject. I get it. So I have no problem spending a little more time here someplace. So to kind of reiterate this one more time, usually your populations aren't this small. So to try and find out information about a population parameter, you take estimates from a sample. So you sample and you get different estimates. We're trying to see the behavior of these estimates. What these two columns are saying is that on average, actually these three columns are saying on average, X bar gives you what you're looking for. The average of all these sample means gives you 80. Okay. The average of all these sample means gives you 80. The average of all these sample means gives you 80. So that makes X bar an unbiased estimator because it's giving you what you're looking for on average. There's another thing that you should notice about X bar. And I wish you were in class, I'd scream it at you. X bar is a random variable. Its value depends on chance. So if you look at our little table here, we have values for X bar between 77 and 83.5 and all kinds of things in between. So the value that you get for X bar is itself a random variable. Now the mean of that random variable is the same as the mean of blank. What would I fill in this with? The mean of this, mean of X bar right here matches what other number? Match that one, right? So the mean of this random variable matches the mean of the population. And the mean of the population is denoted with mu. One other observation to get out of this, and that is, as we increase the sample size, what else happened to these plots? What's decreasing?
The standard deviation.
Yeah, thanks, Nate. The standard deviation. Standard deviation. Yeah, standard deviation decreases. So 3 conclusions that you should get out of this. Now, I'll confess, there's not much in the way of homework that I'm going to give you from this section. I think there's 1 or 2 problems at most, so not a lot. It's a harder section, but it's also kind of a setup section for what we have coming up. All right. Let's see here. Let me give you a little list of different things that we can look at in terms of estimators. So, estimators. X bar, which is your sample mean. S, which is your sample standard deviation. If S is your sample standard deviation, does anyone know what S squared represents?
Sample variance.
Yeah, well done. Sample variance. And then I don't see this notation used very often. X tilde is the median. Sample median. And that might actually be the population median. I'm not sure. We can look at the range. I don't have a symbol for that. Sample range. And the last one is P hat. That's your sample proportion. So I could ask you to help write a conclusion about these different sample estimates and if they're biased or unbiased. And I'll go through and give you the answers in just a moment. But let's try and understand unbiased a little bit more. Because right now, the only example we've got is, oh, the X bar is an unbiased estimator. So we can label that one as unbiased. Well, what does it mean to be a biased estimator? Let's look at the range here. Let's look at the range of some of our estimates. So now I'm looking at this value here. Come on. All right, let's just do it this way. You remember how you calculate the range? How do you calculate the range of a set of data? Nothing? What's the range of this data?
Two?
Not two, or unless
10.
you're looking at this one over here. What's the range of this one?
10.
10. So the range is top minus bottom. So the range here is 10. Let me see if I want to squeeze, I'll squeeze it in up here. Range equals 10. Let's find the range of all our estimates. The range of this one is going to be top minus bottom. That's going to be 2, 3, 5, 10, 1, 3. And again, all I'm doing is I'm doing top minus bottom. 86 minus 78 is going to be 8, 2, 7, and 5. Let's see if we can't figure out what the total is there. So if I total up, that's 10, 20, 24, and 8 is 32, and 9 is 43, and 5 is 48. All right, I think I got that right. Let's see, 20, 24, 34, and 12. I'm getting a different number this time. 20, 24, and 10 is 34, and 12 is 46. There we go. So 46. If I average these values, what do I get? If I average those 10 values, what's the average of all 10 of those?
4.6.
Thank you, Keisha. 4.6. Does 4.6 match this? No, they're just different. So the average value here of these doesn't match that. You can play that game again over here. The sample range here would be 3, 5 minus, or excuse me, 76 from 81 gives you 5, and then 10, and then 3, and then 8, 5, 10, 8, 10, and 7. So for samples of size 3, let's see, it's going to be 18, 21, 29, 39, 44, 52, 62, 69. I don't know, maybe I made a mistake adding that up someplace. That's all right. 69. We get an average of 6.9. And again, that doesn't match this. With our estimates from our population, our estimates from our sample mean, on average, I got the right value. On average, I got 80 here, and the true mean was 80. But that's not happening for my sample range. So that means my range is what's called a biased estimator. On average, I can't use it and get what I expect. So the range is biased. Now the work for the rest of these things is a little bit challenging. So let me give you some of them. Sample standard deviation is a biased estimator, although the bias is small. Sample variance is unbiased. Sample median is biased. And for sample standard deviation, excuse me, sample proportion, we're actually going to look at that and see if we can't figure out if it's biased or unbiased. So my bar for you in this section is kind of on the low side. I want you to know what a biased estimator is and which one of them are biased and which one of them is unbiased. I could also ask you some of the conclusions from here. But like I said, there's not much in the way of homework for this section. I'm going kind of light on it because I understand this is challenging stuff. Let me find, let's see, I don't think you want college algebra. So let me jump over to here. And this is one of your homework problems. Fortunately, you've got spring break coming up, so you get a little extra time, I think, to work on that homework. And basically, it's designed to try and decide if the sample proportion is an unbiased estimator of the population proportion. Now, this is, again, a really, really small example. So I'm going to give it this kind of approach. How many, assuming boys and girls are equally likely, if you have 2 kids, how many girls would you expect on average? If you have 2 kids, how many girls do you expect?
1.
Yeah, 1. And you can see that the population proportion or the sample proportion is an unbiased estimator, or at least I'll demonstrate it this way. I'll calculate the actual expected value here. So there's sample proportion of girls in one column and the probability of that in the next column. We're going to calculate that sample proportion. So if you're sampling from this distribution, you could get 0, and that's going to have probability of 1/4. You could get 1 girl, which has a probability of 1/2, and you can get 2 girls, which has a probability of 1/4. This is all going back to the sample space that they gave you, which was girl, 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 boy, boy, girl, and boy, boy. So you can figure out the probabilities based on all that. If you do x times p of x and calculated the expected value, you get 0, 1/2, and 2/4, but 2/4 is really 1/2. So that's your expected value. It's also showing in its own way that the sample proportion is an unbiased estimator. So that kind of completes your chart here for you. A very simple 3-point question I could ask you is, which of the following are biased and unbiased estimators? And your unbiased estimators are going to include your sample mean, your sample variance, and your population proportion, or your sample proportion, I should say. It's estimating the population proportion. So in summary, here's some major conclusions that you should be familiar with. And this is the kind of stuff, stuff that's off this handout that I could ask on an exam. X bar is a random variable. That's something that, takes a little while to get used to. But when you look at all this section up here, here's all your different samples of samples of size 2. The value of the mean for samples of size 2 depends on chance. You can get some high values, you can get some low values, you can get a perfect value, but its value depends on chance. So it's a random variable. Another thing that happens with this random variable is as you increase the sample size, the standard deviation of that random variable decreases. And it actually does so in a very predictable way, which we'll highlight in section 6.4. But the sample standard deviation is decreasing for each one of these. Finally, what's biased and what's unbiased? Here's your biased and unbiased estimators. Just know those. A biased estimator means on average, you're not getting what you're trying to get. It's not saying it's a worthless estimate, it's just saying you're not going to get, on average, what you're looking for. All right, good deal. Let's give it a rest here for section 6.3.